Computer Science 305 Programming Languages, and today we're going to look at take a look at ML for the fourth time and last time. So, as part of this, we want to look at type definitions, right? So most programming languages are pretty useless unless we can actually define our own types. And so there are the types that we're looking at are predefined but not primitive in ML. So if we open up SML, right, or PolyML if you're on Windows, so you have data type bool equals true or false, right? So we can actually create a bunch of different types, right? For example, we can create a data type constructor for lists. So data type element list equals nil, or cons of element times element list, right? And so basically what these are is they are defined for ML in ML, right? So what we're going to be talking about today are 5 different things, and I'm going to break this down to 3 lectures. The first two will cover the first one will cover enumerations and data constructors with parameters. Second will cover type constructors with parameters and recursively defined type constructors. And finally, the last will summarize and say farewell to ML. So we can define our own types, right? So new types can be defined using the keyword data type as we just saw. And these declarations define both type constructors for making new, possibly polymorphic types, and then finally data constructors for making values of those new types, right? So for example, we can construct a data type called day, right? So pretty simple. Say data type type day equals MON or Tuesday or let's read. Oh my god. We'll get out of this and we'll. Alright, here we go. Very good. We'll try all that again, and I'll move the mouse out of my way so it's not bothering me. Okay. Let's try this one more time. Data type day equals MON or Tuesday or Wednesday or Thursday or Friday or Saturday or Sunday, right? Finally. Okay, so we have this data type. Now we can actually create functions for this, right? So is week day x equals not x equals Saturday, or else x equals Sunday, right? So this is essentially an enumeration, right? We have an exact definition of all the different possible days that we can have, fully enumerate out into each possibility. And thus we can then use that to actually construct functions which give us information, right? So we create this function is weekday, and we ask is weekday MON value is true, right? Is weekday Saturday value is false, right? As expected, right? So day is the new type constructor. Day itself, right, is the new type constructor for the values Monday, Tuesday, all the way through Sunday, and those are the new Monday through Tuesday, etc. are the new data constructors, right? Day is the type, Monday, Tuesday, etc. are the data. So why do we call them constructors? And so we'll see that in a moment, because we can see how they can have actual parameters, right? So if we go back and look at this, we have essentially in our data type day, right, there were no parameters for the type constructor, but and so it can't be polymorphic, right? There's only one day type. So and the data constructors, etc., take no parameters. They are constant values of the day type. So we capitalize, and also it should be noted that we capitalize the names of our data constructors. Furthermore, we also have strict typing, right? So if we create another data type, we'll call it flip, right, which is heads or tails. So data type flip equals heads or tails. So now this has two data type constructors, heads or tails, and one type constructor, flip, right? So then when we ask if this is heads, right, we say function is heads, x equals heads. Now if we look at the type value in here, right, it is of type flip that returns a boolean, right? The function takes in a flip and returns a boolean. Now if we try to use this with a day, right, so like Monday, heads is heads, MON, it will fail, right, because operand was a day and expected a flip, so that's not going to work out. So ML is as strict about the new types just as it is about any other type. Unlike in a C enum, right, no implementation details are exposed to the programmer. So how this actually works is not exposed. It's just something that's available. We can also use these data constructors in patterns. For example, if we wanted to create a function is weekday, and so we have two base cases here, Saturday and Sunday are false, and then anything else is true. We can actually say function is weekday sat equals false, or oh my god, is weekday, sorry, is weekday sun equals false, or is weekday underscore equals true, right? And so now we can use those if we put anything in. So we say is weekday and Monday, right? We'll catch the underscore, and that should return true. Otherwise, we is weekday sat, and that returns false, right? So we can use these, right? In the simple case, they work just like constants. These data types, data constructors, I mean, but we can have more general cases as we'll see coming up here, right? So this moves us into the second part of this, which is data constructors with parameters. So that moves us to wrappers, right? We can add a parameter of any type to a data constructor using the keyword of. So we can have a data type, we call this xint, right? So we create a data type xint, and then we create a value of int, right? So this is basically saying that it extends the int, and then we can have plus inf and minus inf, right? So positive infinity, minus infinity. So in effect, when we do this, such a constructor becomes a wrapper that contains a data item of the given type, right? So value has a value like some integer value attached to it, and then plus inf and minus inf have no actual values, right? They just are kind of understood to be something. So we can create these, for example, as we see here. We can say this plus inf, right, and this gives us of type xint, right? We have minus inf, which gives us another xint, right? Then we have value. Value gives us a different type. It says int. It's basically a function that given an int returns an xint, right? So if we call value 3, we get the value is equal to value 3, right, which is an xint type. Value is a data constructor that takes a parameter, the value of the integer to store. It looks like a function that takes an int and returns an xint containing that int, right, as I've been talking about. So, but a value is not an int by itself, right? A value is an xint, right? So we can't add it together with something else. So if we create a val x, right, and equal to value 5, we cannot add that to we can't add x and x, right? Because the overload, the symbol plus is not overload for xint. So we can't say x plus x, it will fail, right? Because obviously value 5 is not an int, right? It's a function that essentially it's a function type that takes in an int and returns an xint. but we can use pattern matching to get an int back out, right? So we can say value y equals x, right? And then so val y equals 5 int, right? So we can if we return that, right, to recover a data constructor's parameters, use pattern matching, right? So value is no ordinary function. Ordinary functions can't be pattern matched in this way, right? And note that this example only works because x actually is a value here, right? So x is an actual value. So that is a data constructor for xint of type value. And so it actually works, right? We can have an exhaustive pattern for doing this. So now, if we take in, so we create another function. So, or we create a value, val s equals, and we're going to say it's equal to the case where we put in x, right, of plus inf, that will match infinity, right? Or if we have minus inf, that will match negative infinity, as expected. And then otherwise, if it's a value, right, in this case we know x is, right, so int.toString y. So when we do this, when we execute this, it will return the string value 5. So as we see here, though, it did some auto-loading for us. So auto-loaded the basis.cm library, so let's not worry too much about that. But unlike our previous example, which was saying val y, it was val that took in a value y and set it equal to x. In that previous example, right, it can't handle all possibilities that were xint. It only handled the one which is val y, or value y, right? This one, on the other hand, does handle all of them, right? We can create a function, a pattern matching function, right? So, for example, function square, right? And then if we say plus inf, it just returns a plus inf, right? On the other hand, if we have minus inf, if we square that, it returns plus inf as well. And then finally, if we have square on a value x, that should return value of x times x, right? So this would then gives us square, which maps an xint to an xint. So if we call square on minus inf, right, we get plus inf back. If we call square on the value 3, right, then we get 9, the value 9. So pattern matching function definitions are especially important when we're working with our own data types, right? Because we need to be able to handle matching any of our possible types. So this is just handling enumerations right now, right? So there's also, you can do exception handling, right? So there is a possibility that we can have an overflow if we do on a square, right? So if we have numbers that are just huge, we can end up having an overflow, as you saw in ML2, I believe, when I was doing factorials. We had overflows occurring on very small numbers. So if we were to execute this, right, maybe we want to update the implementation of function square. So we say function square. If we see a plus inf, right, we just return a plus inf, just as before. If we see a minus inf, we also return a plus inf. Now, when we actually get to the part that matters, when we're dealing with an actual value, there is the possibility that if we say value x, right, is equal to value x times x, we can actually have a overflow occur due to that multiplication. And so what we want to do is we want to handle that overflow, exception handling, right? So handle the overflow by mapping to a plus inf. And so if we were to execute this, square on a value of 10,000, right, which we would return 100 million, that handles just fine. But if we were to do this on 100,000, we probably would end up with an issue, right? So we call square value 100,000, maybe one extra zero there, and it returns the plus inf, handling that overflow. So we can also use patterns are used in ML for exception handling, as it was shown in this example. When we get to Java, we'll see more exception handling constructs. If you look at the Ruby lab, you also see that I used exception handling when dealing with file I/O stuff. It's easier to understand. We should all know about exception handling. I believe that we teach that in 232, assuming that you've taken 232. Exception handling is one of the most useful things in a programming language, mainly because it helps us arrest the program and keep going while also giving the user feedback, such as via logs or through pop-up dialogues, etc., in a GUI-based application. Or even in a pop-ups or other techniques that are used in web-based UIs. So these types of information are really useful for users to help them understand that they made a mistake when giving us input, as well as to prevent to give an error, as well as provide more information when handling input validation, which is a significant part of secure programming. Things you will either learn about in the field or when you take other courses. So anyway, we'll cover a lot of that in Java. But for now, I'm going to stop this video, and then we'll come back to type constructors with parameters and recursively defining type constructors in the next video for this section.